1, the weight of ammonia circulated in a machine is found to be 21.8 pounds per hour. If the vapor enters a compressor with a specific volume of 9.6 cubic feet per pound, calculate the piston displacement assuming 80% volume efficiency. Okay, we have here an 80% volumetric efficiency. So recalling, the volumetric efficiency is the ratio of our initial volume V1 and the displaced volume VD, which is the unknown in this problem. Okay, we have our volumetric efficiency as 80%. Do we have our V1? Not yet. What we do have is the mass and the specific volume. We know that volume is equivalent to the product of the mass and specific volume. So we can use that particular equation. Okay, volumetric efficiency is 80% or 0.80, equivalent to the mass is 21.8 pounds per hour times our specific volume, that's 9.6 cubic feet per pound, divided by our displaced volume, which is the unknown. What is our VD in cubic feet per hour? Answer is 261.6 cubic feet per hour. When the expansion or compression of a gas takes place without transfer of heat to or from the gas, the process is called adiabatic. Next one, a single-stage ammonia compressor is producing 10 tons of refrigeration and the power consumed is 15 horsepower. Suction pressure is 25 psi. Condensing pressure is 180 psi. Drying temperature is 20 degrees Fahrenheit of drying cooler. Determine the actual COP. Recalling, the coefficient of performance is the ratio of the capacity or QA and the power consumed by the compressor. And those two are both given. Here we have our QA or the capacity, which is 10 tons of refrigeration. And our power consumed by the compressor is 15 horsepower. But take note, COP should be dimensionless or the units must all be cancelled. So we must convert the tons and the horsepower into a unit both common for the feet. Okay, for the tons, we could use 1 ton is 3.5167 kilowatts. So using kilowatts also, 1 horsepower is 0.746 kilowatts. And then cancel. So the units are all cancelled. What is the coefficient of performance? The answer is 3.14. The mass of water vapor per unit volume per area is. Next problem, we are required to determine the total number of tubes to be used in each pass. So inside the tubes, the water flows to absorb the heat from the condenser. So meaning we are required to relate the quantity of water to the number of tubes to be used. Okay, so there's a certain quantity of water to be used to absorb our heat projected from the condenser. And that amount of water is equivalent to density of water times the cross-section area of each tube times the velocity of water inside the tube. So this is a constant and velocity of water inside the tube is given, which is 6 feet per second. While our total number of tubes is inside this area because this area is the total number of tubes wherein the water is flowing. So our unknown is in here. So that is equivalent to cross-section area of each tube times the number of tubes to be used. And to solve that, we must able to determine first the quantity of water because these two are already given. And to find the quantity of water, we must know the amount of heat absorbed by the water. And this is a heat exchanger, meaning there's an exchange of heat between two fluids, and that is the steam and water. So the heat from the steam is absorbed by the water. So in formula form, that's equivalent to the heat absorbed by the water is equal to the heat rejected by the steam. So the mass of water is inside the heat absorbed by the water because there is an increase in temperature of water. So we will be using sensible heat formula. Okay, for the heat absorbed by the water, that will be mCp del T, where m is the mass of water. Okay, so let's identify first the mass of the water. That will be m of water times Cp of water, that is 1 BTU per pound Rankine, times the change of temperature of water. So the exit temperature is 95, while the inlet temperature is 85. So that will be 95 minus 85 degree Fahrenheit is equal to, for the heat rejected from the steam, that is equivalent to mass flow rate of steam times the change of enthalpy. Okay, so the mass rate of our steam is 1 million pounds per hour. Times the change of enthalpy. So our entrance enthalpy is the enthalpy of our condensate, which is at 1090 pp per pound. And our exit is our enthalpy of the saturated liquid at the exit of the condenser, which is 69.72. Calculating that equation, what is the amount of water to be used to absorb the heat rejected from the steam? So that is equivalent to 102,028,000 pounds per hour. So that's the unit of our mass flow rate of the water, because it is the same with the unit of the mass flow rate of the steam. Okay, so we can now use our initial equation. So the mass flow rate of water is 102,028,000 pounds per hour is equal to the density, which is 62.4 pounds per cubic feet. Our area is the area of each tube at the inside, so that will be pi over 4 times inside diameter squared, which is 7/8 inches. So let's convert that into foot. So that will be 1 feet per 12 inches. That will be squared. That's the cross-section area of each tube. So we must multiply it with the number of tubes, multiplied by the water velocity, which is 6 feet per second. As you can see, this is per second, so we must multiply this with 8,600 to make this per hour, because our left side of the equation is in terms of per hour. You can cancel it out, as well as the pounds, as well as the cubic feet. So how many tubes are needed? The answer is 18,127.48 tubes. And from our choices, the best answer is 18,200 tubes. The external pressure applied to a confined fluid increases the pressure of every point in the fluid by an amount equal to the external pressure. This is known as the Pascal's law. Okay, a follow-up question. This time, calculate the total length of the tube to be used in T. So we are required to calculate the whole length of the tube used in this surface condenser. Okay, we know this is a heat exchanger. So for heat exchanger, we have a general formula of Q is equal to UA delta T, where Q is the heat transferred from one fluid into another. So it could be either the heat rejected from the steam, or it is also the heat absorbed by the water. So in this case, let's use the heat rejected from the steam. And that is solvable because we already have the mass of our steam as well as the enthalpies, inlet and outlet. Okay, so our U is the overall heat transfer coefficient, which is already given. That's 480. So this is provided. As you can see, this U is based on the outside tube surface, meaning our A should be calculated based on the outside tube surface. And the outside surface of a tube is equivalent to the surface area of a cylinder. So that is pi times outside diameter times our total length, which is our unknown. So inside our A is our unknown. While our del T for heat exchanger, this is equivalent to the log mean temperature difference, or LMTD. Okay, so let's solve that. Okay, for our heat reject by the steam, that is mass stored in the steam, that's 1 million, or 1 times 10 to the 6 pounds per hour, multiplied by the change of enthalpy, which is 1090 minus 69.72 is equal to, our U is 480 BTU per hour Fahrenheit square foot. Our area is the total surface area, so that will be pi times outside diameter, which is 1 inch. And as you can see, our units are all based per foot. So we have to divide this by 12. So this will be 1 over 12 foot times our unknown, which is the total length of our tubes. So that will be pi times outside diameter times total length. And how about our LMTD? So first, we have to draw our temperature length diagram. And we have to draw the path of our fluids. So let's start with our hotter fluid, which is the steam. So our steam, in terms of temperature, it enters at 1 psia, which is at 101.7. And as you all know, inside the condenser, it is an isobaric process, which is also an isothermal process because the process is condensation. So there is no change in temperature, only a change in phase. So our entrance is 101.7 Fahrenheit, and the exit has the same temperature. So that's our steam. And for the other fluid, which is water, it enters at 85 and exits at 95. And it is required to analyze the differences of the temperatures on each side. So let's start with the left side. That will be 101.7 minus 85. That's equivalent to 16.7. And for the right side, that will be 101.7 minus 95. So that is 6.7. And for our LMTD, it is equivalent to higher temperature difference minus lower temperature difference all over the natural logarithm of higher minus over lower. So obviously, the higher one is 16.7 and the lower one is 6.7. So we can now calculate our LMTD. So this will be 16.7 minus 6.7 all over the natural logarithm of 16.7 over 6.7. So our total length is in terms of feet. What is our total length of the tube to be used in feet? So the answer is 741,521 feet. And from our choices, the best answer is 742,000. The final horsepower delivered to the equipment is equal to or the same as the effective horsepower. Okay, for our final follow-up question, calculate the total length of the tube to be used in feet per tube. So from our two previous similar problems, we have calculated our number of tubes and total length of tubes. So this time, we will be calculating the length of the tube to be used in feet per tube. So from our unit of feet per tube, so obviously, we have to take the ratio of the total length used and the number of tube used. So that is equivalent to the total length of tube that we have solved from the previous problem is 742,000 feet. And the number of tubes used is equivalent to 80,200 tubes. But take note, this is a two-pass surface condenser. So, meaning the total length of tube must be divided by 2. So, what is our answer? So, this is equivalent to 20.4 feet per tube. Pump used to increase air pressure above normal. Air is then used as a motive power. So this is the air compressor.